What's up, what's up? Welcome back. Today we're working on my x86 operating system. It's a Rust operating system that only really runs in a virtual machine right now. If we pop open our little demo UI, I can compile and run this guy. And this opens up a virtual machine, QEMU. We see some logs here, which is it's serial output from my computer that the virtual machine is forwarding here into standard output. We have memory allocations, we have maps and vectors and all that good stuff. We have this little demo game. Oops, there's that crash that I haven't debugged yet. We have this little demo game where we can play Brick Breaker, which proves that we're taking user input from a keyboard and rendering to the screen when we have some sort of graphics going on. Now we have multitasking. So if I go to the IP of the kernel, it says hello, we're running a little web server, and the logs indicate that I'm servicing HTTP requests on different CPUs. So we have multi-core, we have PCI, so that we can talk to the Ethernet card, so we can do HTTP over TCP and stuff like that. And so that's kind of where we're at. We're starting to see something useful, and what we're working on today is we want to work on actually spawning processes. So right now our operating system is really more of just a kernel, and that kernel doesn't really do much other than what we have shown here. And if I wanted to start using this in different contexts with different programs on different machines, I wouldn't really have anything that useful because we can only do what's precompiled in. And so what we want to do is we want to figure out how to load programs in the operating system and let those programs interact with input output and graphics and all that stuff. So yesterday we got this poor man's elf loader working. So we wrote this little program that in Rust will load an elf file, which we've compiled from we've compiled from this guy. So this is a really, really dead simple program. He doesn't do anything except he takes in some function pointers when he boots. He expects that when you start the process that there will be some function pointers available for you, and all he does is he tries to print hello world and then exit. And we have our loader, which we wrote in Rust, that basically looks at the compiled file, figures out where the start of it is, puts it into a reasonable spot of memory, and just starts running it. So if I run cargo run here, sorry, let me get my environment set up. I guess we'll go here and we'll go back to custom loader. If I run this guy, we see a bunch of debug information printed, but the important thing here is that we see our little hello world from the child script running, and this is done without any syscalls in Linux. We're not running exec. We're just replacing ourselves with this new executable. And so, yeah, what we want to do is we want to try to integrate that concept with our operating system and figure out how to replace this print that's happening with something that our operating system supports, essentially. Yeah. So I guess the first thing that we're going to do is we're going to try pulling in elf loader to operating system. Okay, so we'll go into our OS, we'll go to main, we'll look at where is a good spot for this. So when we boot our kernel, we go into kernel main, and we initialize our kernel, and that does all of our driver instantiation stuff, and then we run our little demo, which spawns the longer term things our Brick Breaker demo and our web server. All of that spawned in here. And so probably what makes sense is somewhere in here we'll probably just do a little we'll make a section that's spawning a process, and then we'll have to spawn the process. And that, yeah, we'll probably kind of slot it in here. So maybe what we're going to do is let's make a new file for process, call it process.rs, because it's going to be used to spawn a process. And let's try to figure out like what is that API going to look like. So right now we have like no file system or anything. So it probably makes sense for us to just like embed an executable directly in here and figure that out later. So I figure like we'll load it with the code we write here, but we'll embed the binary straight into our kernel and figure it out. And I guess part of what we have to do there then is we have to actually have an executable in this repository that's like available to run. So probably what we should do is let's just like take the thing that we're loading in our sample over here, and we'll put it in our streama. So maybe we'll put it in res, and we'll call it sample. We'll say make dir sample program. Let's paste it in here. So this is just our like simple thing that like expects a vtable and a star function, and we'll have to compile this guy somehow. So probably in our build script, which doesn't exist right now, we'll probably want to do something like find our compiler. So let's pull in the compiler crate for. Well, does that make sense? Maybe we'll just spawn it manually. Let's do that. So where did we go? I lost my window here. So I think there's std process command, I think. And we want to use that guy. Cool, so we'll use std process command. We'll say command, and I guess I need to figure out how that API works. I don't actually know. Rust up doc open. Nope, I don't have that in this window. Next shell. I guess we'll just Google it instead. Command in Rust. Let's check it out. So here we're going to spawn a new command, which is our compiler. So this is I don't remember, i686 elf gcc. Yeah, that looks right. So we're going to say i686 elf gcc, and we're going to pass in an arguments. So what are we doing in our sample script from yesterday? We have our little build script, and we call this. So we're going to compile it with fpic, where fpic means essentially enable position independent code. So usually, if I understand correctly, each process will like statically assign where its start should be. So every program could have like the same starting address 1000. And when I load that process, I create a new virtual memory space. So each process has its own like virtual memory mapping, where like address 1000 will correspond to different segments in memory, depending on which process you are, right? So you might have like, this is like vmem for process A and vmem for process B, right? These guys will look like essentially the same. I'm spawning the same process. Both of these guys might have their start address set to right here, right? But if I look at like my like actual RAM, like my physical RAM, the operating system will say like, okay, this chunk of memory lives here, but this chunk of memory lives over here, and this chunk of memory lives over here, right? Like, even though to these guys they both look like they have the same address, they have different physical addresses. And so we don't have that concept implemented in our operating system at all. And so what we're doing is we're saying we're going to enable position independent code, and that way even we'll figure out like process A will say I want to start at address 1000, and B will also say I want to start at address 1000, and we'll just be like, fuck you, right? I don't care what you want. I'm just going to put you at address like 9999, and you run from there. And hopefully if you have position independent code, if I've copy pasted you to the wrong spot, you should still work, is essentially why we're doing that. We have to output this guy to somewhere. Let's put him in like our output directory somewhere. So I think you have std env var out. And we'll say let output dir is equal to this guy. And here we'll expect, and we'll say no output directory. Okay, and so now the output file will be format output dir slash we'll call we'll call it sample program.elf. Okay. So this guy will be output to output file. The input file is going to be where are we? We're in res sample program loady.c. So let's rename that guy. I don't like that. So we'll go into res sample program. We'll just rename this guy sample.c. And so this will be from res sample program sample.c. Cool. And this last arg is no stdlib, which essentially says, hey, we're going to do our own shit. Don't link me with libc because we don't have a libc for operating system. Like, just do nothing. Do the minimal thing. And then I think we have to, like, run this somehow. So he says output. Is there, like, a way to discard output? I don't really care what the output is. I just want to... output... Oh, status is probably what I want. Yeah, status. And expect failed to run build for sample program. Okay. So I think that should give us a binary in our output directory. So if I cargo build now, he says no output directory not present. So how do I thought that the output was defined here. Maybe it's cargo out? I have to double check. Cargo, let's look at build.rs. Oh, outdir. Haha. My bad. Okay, so it looks like that built something, and we can look at our target debug build, and there we go. We have our sample program here. Sick. So he's built, he's ready to go. And now what we have to do is we have to integrate that with the operating system. So here we're just going to say const sample process. Finally back again. I got busy with the new reverse engineering projects I haven't joined the past few days. What's your reverse engineering? Reverse engineering is so fun. I've never really got that good at it, but it's so, like, the pieces I've done are, like, very, very satisfying. Just doing something, like, dead simple. Mwah. Like, it just feels so damn good. Okay, so this is going to be a U8 slice, and he's going to say, I'm going to include the bytes of the compile time environment variable outdir concatenated with the string sample program.elf. And that should give us something that is buildable, and that constant should be accessible in our program. So now what we should be able to do is we should be able to start making, like, our elf parser. We should be able to pull that in from our stuff from yesterday, and we should be able to, like, start parsing information from it. So we do need to pull in that elf crate we're using. So let's quickly look that guy up. 0.7.4. And again, I'm willing to eat this dependency, even though I usually wouldn't, because it is, I would assume that these are, like, complicated enough that I don't want to deal with it. What do I have to disable some features to work in no std? Features, default or stood and to stir, and I guess I just want to say no default features. So say version here and no or default features is false, and this should compile now. Cargo build. Reverse engineering the camera app of Android of a camera that failed like 10 years ago called the Light i16. Interesting. I guess the bright side there is if you have the kernel code, there's a lot that you should be able to get for free. I guess any, like, user space post-processing you don't get, but even just, like, tracing syscalls should get you a long way for, like, how are you interacting with the camera at all. Cool stuff, cool stuff. Okay, so it looks like that compiled, the elf crate compiled, and so now we can start making our struct. So what are we going to do here? We're going to have like a struct process loader, right? I'm going to assume that it being a struct makes sense, but maybe we could get away with a free function. Let's see. Let's try free function first, I guess, and see how far we get. So we're gonna look at the reference from yesterday. So this is gonna be what it said: custom loader source main. And in our main, what do? We like read the file, we map some memory, and then we jump to that spot. So I guess it's probably fine to like not put this as a structure for now. So we'll say function run process, and he's going to take in a bunch of bytes, and we'll call this like elf file. It has 16 cameras. And it takes a picture with 10 of them, but we want to use all 16. That's pretty cool. Pretty cool. So here we're going to use the elf crate. I guess we don't need to type that here. And we're going to first parse the elf in the same way that we did here. So get min max mapped address. That's going to be still used. This gets the minimum and maximum addresses that are attempted to be used in the program. We're going to skip all this part about like reading the file and figuring out page size and stuff. We don't care about any of that. But we do care about the part where we open the file. So here we'll say that the data is minimal parse of the elf file. We're going to extract the minimum and maximum addresses. Great. And then we're going to allocate a range for this. So we're going to say, what? I guess we're going to make a U8 slice. So we're going to say vec U8. So we'll say let process memory is equal to vec U8, or process memory is probably wrong. Mapped process, we'll call it. And we'll make this a new vector. And here we can do the same thing that we did in this program, which is we iterate over the segments of the binary. And for each segment, we just have to put those into the map process. So here, I guess our map process, we're going to have to preset, we're going to zero it out for the size of max adder minus min adder. Cool, so we're going to have to use alloc vec, the vec macro here. And this needs to be converted into a usize. Great. So we'll say try into expect failed to get, let's see, process space bigger than usize allows. And then all we have to do is copy these segments in. So we're going to copy from elf file, but instead of doing this like pointer copy that we did before, we're going to say mapped process, and we're going to go into the mapped adder till the end of the file. And we're going to say copy. I think we can copy from slice here. This needs to be cast to a usize. So say mapped address does not fit in usize for now. And what APIs do we have? I think there's a copy from slice. Nice. And where we're copying from is the input file from the offset of the segment. So we'll say let source start is segment offset as usize. We'll say let source end is equal to source start plus the size of the file, so segment.p file size as usize. And so we're going to copy from slice, segment, source, start, dot dot source end. Like this. Cool. We need to make sure that this is a U8 vector. Cool. Okay, so I think that that should all be fine. And so at this point, we should have a chunk of memory that we could just start running code from. And it should work. So can I just like pull in that assembly to jump to that spot from this guy? So he had this like load process function, and we need to use core arch global assembly. I'm sure that this jump actually is not quite right anymore, but we'll live with it for now. We're going to pull in this vtable, which matches the definition that we have in our C file, and we have to like stub this guy out in the same way we did here before we jump. And this like load process thing is going to be the same. Okay. So this guy is the mapped process as pointer add. Okay. So he thinks that the load process function doesn't exist, so we need to tell the compiler that there is a load process function and it's defined in assembly, or I guess he doesn't care that it's in assembly, he just knows that it's external. So we do that by dropping an extern C block in there with this load process. Boom, boom. And now we have to define our print and exit functions. So I don't actually know how we're going to do exit. Exit's going to be a little tricky, but print should be easy. So we can just do the same thing that we did in our sample program where we did C print is like this and C exit. We were just going to have to maybe panic. We'll say unimplemented, exit unimplemented. Okay. Cool. We underscore here, and now we just have to make this run process function public. And this guy has to be unsafe, like this. But I think otherwise this might work. Might not, probably won't, but it might. So we can go back to our main here, and let's look at in our demo function where we say spawning a process, can we just call like process run process with the sample process? And let's try running this and see what the fuck happens. Almost certainly something really bad is gonna happen. Oh shit. So this assembly that we wrote yesterday for loading a process, this was a how do I say this? This was using the 64-bit calling convention and 64-bit registers, which we don't have. So we're gonna have to do the 32-bit calling convention, which means that we'll, if I remember correctly, this is using cdecal. And if I remember correctly, arguments are on the stack right to left. So yeah, callie 1, 2, 3 is push 3, 2, 1. So the first argument is the last thing on the stack. So we're actually going to swap the argument order for this way. So we're going to say that the buff of where we're going to want to jump to is the first argument that we can pop, and the vtable will be the second one. And the reason we can do this is the reasons to do that is that we can now say pop into EAX and then jump to the thing in the address stored in EAX. And now we've only popped one of our two arguments, right? Which means that the vtable, which is our second thing on the stack, will be the first thing now. And when we jump into our start function, the vtable will be the first and only argument that we pass in. I think. We'll find out. So now we have to swap the arguments. So we just go like this, and then we paste it over here. We put a comma, and we delete the other comma. And now this should compile, and will probably almost certainly crash. Oh, we're having a linker problem. Undefined reference to strlen. So sometimes we end up with Rust code that calls into like the standard library, but sometimes like that standard library doesn't exist, and so we have to implement some of those functions. We've kind of implemented some of these before. We did implement strlen as part of our Doom exploration, so I think I can probably just pull that same implementation. It's probably fine. It's probably fine. Strlen. So what do we do? Yeah, that looks fine. That looks like a fine implementation. So we just say, look for a 0, and when you find it, get the fuck out of there. So do we compile now? Wonderful. And do we crash? Certainly. So source slice length does not match destination slice length. So that's probably coming from this copy from slice. These guys probably actually have to match perfectly. So here we'll just say let dest end is mapped adder plus the same size. And then we'll just put a little dest end in here. And hopefully that copy will work. And we did end up getting through this, but we didn't see our like process run, I guess. Like we didn't see the print line that we expect to see. So it'd be interesting maybe to throw like an unimplemented in here and say print line unimplemented and see if this crashes. Nope, no crash. So that's kind of interesting. And so maybe what we want to do is kind of pop open GDB and see if we can figure out what's actually happening here. So we're gonna run.gdb and we'll just set a little breakpoint here. This is target debug kernel, cool. And so what we do here usually is we say we run our like script with like this environment variable gdb equals 1. And so what happens there is we have this like wrapper script that we're actually running. When you run cargo run, it puts the output through this guy, and this guy sets up QEMU with all of these like extra commands, whatever. And one of the things it does is it says, hey QEMU, can you act as a GDB server, keep track of like your instruction pointer and memory and all of that jazz, and then forward that over to another GDB instance. So we're gonna say cargo run with GDB equals 1. Then in this window, we're gonna say GDB use that script. And what we've kind of noticed before is, sorry, one second, I'm in the wrong directory, is that this seems like a little bit broken. So what I've had to start doing is I spam Control C, and that lets me actually hit breakpoints. Otherwise, the breakpoints don't work correctly. And so I guess what we want to see here is we want to see that our mapped process looks like the disassembly of the process we're trying to run. That's the goal here. And so if we look at the mapped process here, and we look at like the memory inside here, do you think you're going to implement your own GDB server at some point? I think that if I ever end up trying to port this to real hardware, I might have to, unless, I don't really know how like JTAGs work and stuff. But I know like the Linux kernel has a GDB server built into it, and it's for the purpose of like, I've used that before when I was working in embedded. It was really sick. When you had like early kernel init problems, you could like run a GDB networked server in the kernel and then like breakpoint on early init, and that made my life so much easier. So it seems possible if I start implementing it on hardware, but for right now, like since QEMU has it built in, there's no really real reason for me to do that, because QEMU is giving me everything I need. Okay, so this guy inside him, we're trying to find like the memory of the process. So do I like dereference this guy? How do I find what's inside? Pointer.0 buff. Oh, here we go. Maybe buff.pointer and dot pointer. Here we go. Here's the data. And we're going to dereference this guy. Oh, he's claiming he's not a left right pointer again? Jesus Christ. So we'll dereference this guy, and we'll print in hex, and we'll print for like 100 bytes. And we'll just see if this matches the disassembly of our guy. So somewhere in here we have target debug, and probably in our build we built a kernel, and here's our sample program. And here we can say obj dump -d sample program. And let's just kind of look at and see if this matches at all. So we see hex 55, 89, E5. So that doesn't match at all, right? We have 7F45, 4C. Oh, but I guess we should maybe read elf everything of the sample process and kind of make sure that the loading is correct. So we have, let's see, we have multiple loaded segments. So maybe let's write down what the segment mappings are that we're trying to map, and then we can kind of compare those, I guess. Yeah, I've implemented one before for a game that rejected WinDebug access. It's blissful to have one. That's pretty cool. How, like, is it that hard? I imagine maybe actually it's not that difficult, right? Maybe all you really need to communicate to GDB is like your stack pointer, your program pointer, or like your position, what is it called? Instruction pointer, that's what I'm looking for. And I'm assuming that like some way to access memory, and maybe, is that it? Like, and registers, I guess? It's not too bad for the most basic of things. Yeah, all right, cool. Pretty cool. Aren't those first 4 bytes the elf signature? They might be. Can we print them as characters? Can we say like dereference this guy as const_car? Right, my process isn't running anymore. Aren't those first ones? You're just saying they are. All right, well, then that means that we're probably doing either shitty mapping or correct mapping. So, oh yeah, sorry, you're right. Good point. We should. We don't know that where we're trying to jump to in this guy. So let's check the start address as well. So we'll say print line offset for start is equal to this guy, and that's just going to be the amount that we're adding in here. So we're going to copy this here. And then let's cargo run again, and we'll run GDB again, and we'll hit Control-C and then continue again. Okay, so the offset for the start is 116. So we should do the same print that we did before. But we want to offset this by 116. Nice. Okay. And then here, does this match the disassembly now? It might. So we have 55, 89, E5, 83, EC, 08, E8, 2D. Okay, so all of that's looking reasonably correct, right? We do seem to have the right thing. It's possible that we're not doing our, like, when we call, maybe just doing like a hard jump isn't the right thing to do here. Maybe we should be executing call. Maybe that's different. So maybe we'll try that. Or maybe what we should do is like, let's break on this and step by instruction, actually. I like that better. And we'll see what actually happens there. So we hit this, we hit C, and then we say next instruction, please. And can we write disassemble and just see what happens? So where the fuck are we? We're, well, we're still in what it thinks is load process. So it jumped to 1B, 7C, 7C, and I don't really know if that's anything interesting. Let's rerun this. see if we can gain a little bit more context. So we're going to say source run.gdb, hit a breakpoint, hit C, and now we're going to like say, where the fuck are we? And we're at kernel process, and we're going to hit disassemble just to see where we are. And it looks like, wait, sorry, let's backtrace again. Let's go up one. We're in kernel demo. Down one, we're in run process, line 74. And can we print like the address of this function? Is that something that we can print from GDB? Okay, that's here at 1B7600. Can we print, maybe we can print the address of load. What was the assembly block called? Maybe we can print that address and that'll give us some sort of clue. So can we print the address of load process? Is that gonna give me something? No. Fuck. Where are we? So we are right before this call to vec. Load effective address 144 off of ESP. Where's like my like jump in here? This is call as pointer. Okay, so we're not quite at the load process point yet. It's down here. This is where we're interested in. So this is where we actually jump to the load process instruction. So let's breakpoint at this address. Continue. And now our instruction pointer should be right before that call. Great. And if I say next instruction, please, we should now be... Oh, he just like jumped and jumped back, which is pretty odd. Do I have to say step instruction, not next instruction? Is that the wrong thing? Fuck. We'll gotta run this again. Let's see. So we'll run it again. Source it again. Hit the breakpoint, hit continue. We're gonna break at the same address we did before. So I think that was here. Disassemble. Double check where we are. Okay. Not where we want to be. I want to be at the call to load process, which is here. So we're gonna break at this guy. And continue. We are now at that address, and now is it step instruction? There we go. So now we're in load process. We can disassemble, and we are about to pop EAX. So we're going to say next instruction, disassemble. So now we're at this like jump, and can I maybe see? Let's see like what's in EAX. So EAX has this address. So what if we disassemble what's there? We should see the start function of the elf we're trying to load. So I think it's disassemble this guy to like this guy plus 100. And that actually doesn't look right. Which kind of indicates that what I popped isn't what I thought. So let's maybe look at the stack pointer, and can we say like what is in this guy? I guess do I have to do like some sort of function prologue at the beginning of this guy? Let's look at that example for the cdecal calling convention again and double check we got this right. So he saves the old call frame. Oh, this is the caller. What about the callee? cdecal, it's, I think if I remember correctly, it's caller save. Subroutine arguments are passed in the stack. If return the values are integer values or memory address, they are put into EAX register by the callee register, whereas floating point values, blah, blah, blah. Registers EAX, EDX, ECX, and EDX are caller saved. The rest are callee saved. Yep. Yeah, so I thought that the callee should just have this, unless call is doing some extra pushing that I have forgotten about. The caller can stack after the function call returns. I guess we can just look for what we expect the arguments to be on the stack, and that will inform us of what the calling convention should be. Oh, I think I'm just an idiot. Arguments are pushed right to left, so we actually should have popped... sorry, let's see. Push 3, push 2, push 1. So if we pop now... Yeah, we should have popped the first argument, which should have been the buffer. So, okay, let's run this again in GDB, and we can write down the addresses, or maybe we'll just print them out here. That'll be easier. Let's write down the addresses of what we're passing in, and then we can use that to deduce where on the stack those things ended up. So we'll say print line argument 1 is this shit show. And argument 2 is the vtable address. Okay, so we'll throw this guy here. And now if I rerun, there is some bracket issues. Where am I missing? So, oops, I forgot to delete some code here. There we go. And otherwise, this match up. Yep, brackets are all lined up. And we need to put this as debug. And this also has to be formatted as debug. Okay. So now we can say source run GDB and smack Control C, hit continue. And now, oops, I'm supposed to, okay, fuck. These aren't printing fast enough. Can I like break it like load process? That'd be nicer. Can I like just say here, break at load process? That makes my life much, much, much simpler. So run with GDB, and we gdb-x run.gdb. We hit the Control C a couple times to make sure that it works correctly, and we are now where we expect to be. We're at load process. Okay, so here we see that argument 1, which is where we're trying to jump to, should be this guy, and we can say, well, let's look at the stack. So we can print our registers. The stack pointer is in ESP, and we can say, what the fuck is in this guy if we were to process him as a bunch of ints? So let's say cast this to a i32 pointer, dereference it, print as hex, and maybe print like 4 things. And so what we're trying to find is we're expecting to see argument 1 of 7fbe blah blah blah, which is here, and argument 2 is this guy. So there's an extra thing being pushed onto the stack before we get to the arguments, and I don't know what that is, which is surprising. Maybe it's the frame pointer. Let's see, like, can we look at like x86 call instruction? Maybe it will tell me somewhere that that does something extra. When executing near caller, he pushes the EIP register, which is the aha. So the first thing that we get from the stack is actually supposed to be the address to return to. So what I should actually be doing is I also shouldn't be popping stuff, because I think that somewhere like the return call will automatically pop if I remember correctly. And so I guess what I should do here is I should look at the values. Okay. I think I get it. So here, instead of popping EAX, let's say Is there like, there's like a load instruction. Move? Is move what I want to do? Yeah, move ESP -4. Is it minus or plus? Plus. ESP +4. And I think, how do I do this in AT&T syntax? I think it's with brackets and a star. So we're gonna move the thing at ESP +4 into EAX. We're gonna push. We're gonna +8 into EAX. We're gonna push EAX, and then we're gonna move the thing at ESP +8, which is now what used to be ESP +4, into EAX again, so that this is now the vtable address. Then we're gonna call EAX here. And I think that might do the right thing. Maybe. Not sure. But we can always try and figure it out. So let's run with GDB again. He doesn't like that. What doesn't he like? Expected register here. Can I not, like, what's the x86 instruction? Load from memory into register. Move. Oh, this is like not the right language. x86 assembly. Wrong syntax, I think. Yeah, that seems likely. AT&T syntax load memory to register x86. That should tell me. This is for x64 though. I want x86. I swear if let's move. Oh, I see. It's the offset bracket the register like this. Yeah. That looks familiar. Cargo run. And GB-X, and we hit Control-C, we hit C, just so that we get this guy looked at. And now we should see just jump existing bins. That would have been smarter, yeah. So what we should see now is after we run next instruction, EAX should have the vtable in him. And so if we look at info registers, we should see EAX with the address of the vtable. Perfect. Now if we run next instruction again, where the fuck are we? We're about to put the, now we're trying to put the address to jump to in EAX. So if we put here, we should see the address that we're trying to jump to. Great. And if we print the thing in the stack pointer, which is this guy, the stack pointer should have the vtable as the last thing on it. So here we should say print this as const i32, and we dereference it, and we print it as hex, and that is this guy again. Okay, so now I guess we just step instruction and see where we end up. Okay, let's just hit continue. Let's fucking go, baby! Okay, that's so sick. Okay, so we got to the attempt to run our print line. It didn't fucking work because we wrote unimplemented. And so now if we run it again, well, we fuck GDB. We don't need anything. We don't need your GDB. We can fucking just look. We should see that print happen. Oh, baby! Let's go! That's so sick. That is so sick. Oh, yeah, I'm pretty happy with that. Okay, so what have we just done? We have compiled a sample program, which is called sample.c. All he does is he has this start function, which is like linked to, like the linker will pull together. He'll put it in, he'll say, hey, here's the start address. We've compiled it with position independent code so that we can put it anywhere in memory without worrying about like a virtual memory addressing. And we've said, hey, you're going to pass us in a function that we can call, and we're going to call that with hello world. And he calls it with hello world. Pretty fucking sick. We now have to figure out exit, but yeah, that's pretty solid. I wonder what happens if I press return here. I wonder if everything will kind of like flow together nicely, right? Like if the rest of our kernel runs at this point, stack corruption, baby. Don't know what else I expected. Because it's up to us, the caller, to pop the thing we pushed on the stack. So I think we can just say pop EAX. I don't know if we have to pop to somewhere, if we can just pop anywhere, but we'll just pop to EAX for now. It doesn't really fucking matter. And maybe then everybody else will kind of work correctly? Maybe? No, but maybe we're getting closer. What do I need to read to take a look at, understand the shit he's doing? That's a good question, because I don't understand what I'm doing, so who fucking knows? I've been reading a lot of the OS Dev wiki. If not to plug my own stuff too much, but I've been uploading like kind of like the whole series to YouTube. So if you wanted to like take a look at like where we started, there's like a playlist on the YouTube channel that's linked in the Twitch description that like you could start at the beginning and see like, well, what the hell is going on? There's also a GitHub linked in the Twitch description that should have this project on it. You could just kind of like look through commits from start to end, and maybe that would give you a bit of a clue. But in terms of like books or anything, we've just kind of been poking and prodding and seeing what happens. Are you planning on avoiding syscalls altogether? Well, okay, so for now, given that we don't have a user space, we've never made it into ring 3. The concept of like triggering an interrupt so that we have a syscall to jump back, I don't like that conceptually. If we get into ring 3, we will need to have like some sort of permission switching mode to get back into ring 0. So probably we'll have to do something there. But I do like the idea of not exposing the syscall interface to the programs, right? We could hide the syscall API behind these virtual functions, and I like that idea better. I've also been kind of toying with the idea of, I like the idea of IOU ring, where like you don't call a function to jump back into the kernel. You ask the kernel to do something later, like queue up a write of some sort, and then wait for it to finish and check later. So we might experiment with that at some point, but who knows? BTW, can you not just use Intel syntax? I could, but I don't know that either. I don't know either Intel or AT&T syntax. So AT&T syntax is what GCC has been using by default, and that was kind of like what the first sample code that I pulled was. And so that's the one I'm using, but I don't really understand one better than the other. Is this some sort of Handmade Hero-like series? If you know about it, of course. I don't know what Handmade Hero is, but this is some form of series, I guess, because I've been streaming kind of like the whole process, so... if that's a yes, then yes. Hold on, I just looked at my screen and I'm realizing it's like dark as fuck. My whole left side of my face is like pitch black. I'm just gonna go turn on the light. I'll be right back. 1 second. That's a little better. Still not great, but good enough. Good enough. Okay. So now, what's the next thing we want to do? We want to be able to return from these. I guess we'll consider this done, and we'll say that like at some point we got to running the executable. And the next thing that we want to do is probably do something like figure out how to exit. How do we get back into the operating system? The Intel one is more readable to me. I would say that I like the ordering of AT&T syntax. The fact that AT&T goes source dest instead of dest source really like helps my brain out a lot, but there's a lot of stuff that's like more confusing. I don't like having to like, I've made a mistake so many times of forgetting to put like the $sign in front of a variable to make it like a number instead of an address. And like that distinction in Intel syntax, they have like the square brackets, and that makes it a lot clearer what the fuck is going on. But yeah, I don't know. I don't understand either, so I'm not in a place to give a pros and cons. I like the fact that you're exploring other routes and syscalls. It's not because of anything. Let's just say it's because I don't understand anything. So I'm just kind of like reaching for whatever's closest and hoping that it works. I'm sure at some point we'll figure out why the syscalls are important and we'll have to implement them at some point. But for now, we're at where we're at. Okay, so let's figure out how the fuck we're supposed to get out of this guy. So, let's go back to this like x86 calling convention thing and see what he does. After he calls, he removes the arguments from the stack and he puts his return value. So I guess at the beginning, we should be able to set the stack pointer should be basically right before the return value. So I guess we should in our let's look at process rs. So here he copies something off the stack. I guess if we look at the stack pointer here, we should be at the exact same point when we try to return. Oh, we also just don't call ret. That's honestly probably the bigger problem here, is that we never try to go back to the function that we were in before. Why KDE? Okay, so this is like a long story that basically boils down to when I tried to play first-person shooters at 144 FPS, KDE on Wayland is the only one where I didn't notice micro stutters, and so that's why I'm stuck on KDE now. Here it doesn't matter, but that's why. You might also find that syscalls are ancient tech and we might have better alternatives in 2023, 2024. That also seems possible. Like, I don't like the idea of taking that overhead when you don't have to. I also don't know nothing though. Yeah, we're in the same boat. Okay, let's cargo run again and see if we get out of this function back into the normal operating system. Woo! Let's fucking go, baby. That's sick. So what this just proved, like the fact that the rest of our kernel ran okay, means that like jumping into this program and getting back out of it worked, which is pretty sick. The next question is if we wanted to implement, do we want to implement the exit syscall? Maybe not. But if we did, what would we have to do? We would kind of have to keep track of where our stack started when we loaded the program, and then jump back to that position and then just issue a return. Which doesn't seem crazy. That doesn't seem too crazy. Is that like the most important thing to do next? Sure, yeah, let's do it. So let's go into our sample program, and let's say that he has some like static memory. Oh. What happens if I give him static variables? I guess that those will get stuck in BSS, and they should be at they should end up in the allocated memory for our process, I think. So I think that should be okay. And we can say like function exit is going to essentially, with the exit code, int code, and sorry, function, what am I talking about? Void exit. He's going to take in an integer, and he's just going to call exit. And do I have to like when I call functions in C, do I just write it like this? I think so. And then we can say static, it's void star exit int is equal to null pointer initially. I guess we have to write 0. And then here on start, we'll initialize this like exit variable with vtable.exit. And then we'll make a function called like void print and exit. Who's going to, I don't know, I guess take in nothing. And we'll do the same thing with a print function, where we have a static variable print who takes in a car star, and we'll have a print function that takes in a car star, and he just prints the string. And then we'll do the same thing here where we say print is this guy. These guys need arrows. And then here we should be able to say print hello world and exit 30. And then maybe we'll also huck in a little bit of a panic. That way we can say that we'll panic here. And we'll put a little angry face. And that way we can say, well, if we get to that point, then we fucked something up, essentially, right? We want to make sure that like this exit means that no other parts of the program run. And so we'll do the same thing here, where we say panic takes in a car star, and panic calls the panic. We'll add a panic entry to our vtable, which we'll have to do on the Rust side as well. Eventually, we also will have to pull this into like a generated structure, right? Like the fact that we're keeping these guys in sync just by guessing is fucked, right? So we'll have to do that later. And I guess first, let's just double check that the panic works. So we won't try to exit. We'll just hope that we crash. And then here, we'll call print and exit. Here we need to set panic is equal to vtable panic. Cool. Cool. And we go back to the process stuff. We add a panic entry to our vtable on this side, wherever the fuck our vtable is. Struct vtable here. I couldn't find it because I was looking. I think my brain was searching for Rust casing, and it just wasn't there. That's pretty funny. So this is a function that takes in data as a const i8. And it's going to look very similar to the print, but he's going to be a panic. He's going to pull the thing from a string, and just instead of saying print, he's going to say panic. All right. Then we say panic is C panic. And now when we run, I hope that we see a panic that says that we see a little angry face. Very nice. And the rest of the code doesn't run. Okay, cool. So now the question is, what the fuck do we do to get the stack back? Someone subscribe with Prime. Thank you for the Prime. Appreciate it. So I guess before we load the process, maybe we at this point here, sorry, I'm thinking. So we're gonna have to have some location in memory that has the like start of our stack for this process essentially. Any static memory in the program will get automatically cleaned up, I think. Maybe. Right? If we were to malloc in the process, we would probably have to keep track of all of the mallocs that we did and remove them after. But luckily for us, we can't malloc from within the process because we haven't given that function in. So fuck you, like, get fucked. You can't do that. So I think all we have to do for exit is essentially like jump, like set our stack pointer back to some saved value and return. And we can probably set it to whatever it is right here. Let me think. Well, no, because this guy's gonna have some like extra cleanup to do, right? Like we've like done something like allocate a vector in here, so we kind of want it to be where the stack, what it looks like here. So I wonder if we can just like set up a variable in BSS, which is like static memory, and can we just like make a variable here? How do we do that? I don't actually know. I guess we would type like label. We would put a label that's like save stack pointer, and this is just going to be like a long of 0, I think, right? So we're going to say like put the number 0 at this point, and then I think we can say C exit is going to be a global function. And he's going to take the value at that spot. So he's going to say, like, move the thing at saved stack pointer into ESP, like the register for the stack pointer, and then just read. I think. That seems fucking reasonable. And then here, like, we'll just pretend that we're returning from load process. So here we just say move ESP into saved stack pointer. Now, obviously, this won't work for multi-process, but we don't give a fuck about that right now. Yeah, blaze it. Let's see what happens. So we're gonna have to actually say that cexit is we're not gonna implement it here now. We're gonna say that this is an extern function cexit, and we're just gonna lie and say that he takes in a exit code. I guess we actually have to keep track of that. So we're gonna say code is a i32. He returns nothing, which means here we actually have to pop. Do you have to pop the i32 from the stack? I guess our exit should take in nothing so that we don't have to do like, because I think that we saw in the C decal calling convention that cleanup is from the caller. Oh, fuck. Which means that if we're actually returning from load process, we actually have to have the same amount of stuff on the stack as when we called load process, which we will because the stack pointer will be there. So I think everything works out. I think everything works out. And so I guess if we take in a exit code here as an i32, here we just have to pop that thing before returning so that it looks like, oh no, we don't have to pop shit because we're resetting the stack pointer. So we can do anything we want. We could push in like 50 arguments. It wouldn't fucking matter because we just increment the stack. Okay, boom, bang, bang, boom. So all we have to do is pop into EAX so that the exit code is returned. And then we can pretend load process returns an int, but we won't worry about that right now. Yeah. So I think that just works. Maybe. Undefined reference to cexit. Okay, so I forgot to write cexit like this. Okay, so we do still see the angry face, but I think that's because we forgot to update our sample program to actually call exit. So the moment of truth here is if we see the rest of the kernel run normally and we don't see the angry face, we're fucking chilling. Okay, so instead, we just fucking crashed horribly. What's interrupt handler 13 again? We need to look at the OS dev CPU exceptions. 13 is a general protection fault. So it's just a seg fault, essentially. So we just hella fucked up. That's okay. Let's maybe put a breakpoint at cexit, which is in run.gdb. We'll say break at cexit. And I guess we should also break at load process, and we can compare. We can keep track of what happens. Yeah, it seems reasonable. So we'll run with GDB. We'll source our GDB script to set up our execution environment stuff. We'll hit Control C to initialize this guy, and we'll say, what is our stack pointer here? Stack pointer is this guy. And so now if we continue, we should be in cexit. Great. We should say info registers. We should see the same value here. So we see ESP of 275 EAC. And so we do see the same thing here. So the question is, when we return now, should we not be in a reasonable spot, right? Like, because if we didn't do any of this stuff, right, and we just called red, we should be in the exact same state now as we would have been then. I think. Okay, so now we are in process again. If we continue, we get a general protection fault again, which is kind of fucked. So let's try something else. Let's here just return. Do nothing else, only return. And let's just see what happens. No GDB. And in this case, we should see the kernel run successfully, which we do. And so the question is like, what if we just move into the save stack pointer, then return? Also great. So if we then call cexit and then don't return, do we see again it working correctly? Yes. So the question is, why is this different? Oh. I wonder if we're getting a general protection fault because we're trying to dereference 0. That seems very possible. In our... Sorry, let me make sure that I'm in the right spot. It's possible that we didn't initialize everything correctly over here. So if we look at our sample C program, panic, exit, print. Oh, wait, no, we do know that we got into the C exit thing correctly because we stepped by instruction and we got there. And so then we were general protection faulting back in the Rust side of things. Thinking. So process.rs. Let's simplify. And let's just only call exit here. And see if that changes anything. Still a problem. A different problem. Interrupt handler 6, not 15. Oh, oops. Obviously that's not going to work because we're dereferencing null. vtable exit. Oops. Okay, so we're still seg faulting. So that means that our implementation of exit is just must be wrong. Let's double check if our C exit here is right. Yeah, it is. Okay. It would be interesting to know. Let's not do this pop just for shits and gigs. Still no. I'm pretty lost. Thinking. Can we? GDB is almost certainly where I want to be right now. I want to be in the debugger looking at registers. And so let's go back there. And we'll rerun again. Oops, I have to be quick to press Control C or else things don't work correctly. So we just hit C again. There we go. And I am in this function. And this function, he is moving ESP into this memory address. And then if I disassemble C exit, he is moving that thing back. So unless somebody else is corrupting what's in there, which we didn't see. Oh, we have to restore registers too. Yeah. That sounds right. Because I think we saw somewhere that there are some caller saved and some callee saved registers. So I think there's like a push AL instruction to just say like, put all of my registers on the stack. Push A, push AD. Pusha. So I guess we can just say push AD and pop AD. So here, before we save the stack pointer, we'll say push a duh. And then after we restore it, we'll say pop a duh. And then all of our registers should be in the same state, and maybe this will work again. Nope. He doesn't like popita and pushita. Maybe I just write pusha instead. Invalid, and let's just, well, I'll fucking Google it. Nope. Okay. How do I push AD x86 GCC? Like, there must be... Am I high? Push AD, pop AD is 32-bit only. I should be in 32-bit. Pretty sure. I'm compiling with a... Oh, real mode instructions. Oh, is it push AL? Push A, x86 protected mode, push all registers. It does seem like that's right. They're pushing EAX, ECX, EDX. What am I missing? What am I missing? It's very possible that just like the GCC like assembler name for this is like not the instruction name. And I don't know how to like look up those mappings actually, which is like kind of fucking stupid. I should know how to do that. Push AD, pop AD, missing. Okay, sure. So they're saying push AL, pop AL, which is what I remembered. But then when I Googled those things, I didn't see them, which is, okay, whatever. Pop AL, push AL, cargo run. We won't run with GDB. And we'll see if we get far this time. So it's just like way more fucked. That's really funny. Oh, it's because these guys are wrong. These register moves now that I've done this big push out is fucked. So we actually want to do something like, before we do that, move the old stack pointer into EBP or something. I don't know. I'm sure I'm misusing this, but we'll deal with that later. Let's see. Well, we can just double check. What the fuck is this guy supposed to do? C decal x86. Because there's this guy saying save the old call frame, initialize new call frame. Okay. Yeah, okay, fine. Yeah, that's fine. That's fine. It's fine. Maybe. I guess we'll see. Still no bueno. Oh, because push all, save the stack pointer. Okay, let's ignore all of this stuff and just try to call C exit. And hopefully that should work okay, I think, if I did this right. Okay, so that's good. I think that before this... oh, maybe this always worked. That might have always worked. I can't remember. Okay. So it's also possible that there's another problem that I'm missing, but let's first see. So here we need to back up the stack pointer. Or do I know how far a push AL moves us? 1, 2, 3, 4, 5, 6, 7, 8. So can we just say like 64 plus 8 is 72? Like, let's just see if that lines up. I guess fine. We'll actually look. We'll use our eyes and our brains and actually look at what the fuck is going on. If you'll make me. Okay, so we're in load process. We are going to info registers. We're going to look at ESP, right, the stack pointer. Let's see what the fuck is in there. So we'll say print as hex. The stack pointer. Oops, I didn't copy it. The stack pointer as a i32 pointer. Dereference it. Print 5 things. He doesn't like that. Oh, because maybe it thinks we're in C syntax now. This shit's so confusing. It's like depending on where it is, like it might try to auto detect Rust in C. Yeah, so here it's in C syntax. So print 10 things. We know that we should expect to see this guy here, this guy here. Everything's hunky-dory. We say next instruction after the push AL. So here we just moved pusha. And let's look at the stack again. So now we actually need to look at the stack pointer as address. So we say info registers. And now we have moved here. So here we pushed some things to the stack. 1, 2, 3, 4, 5, 6. And so we're kind of looking for where we saw df88, df88. So it's here. Which it should be 1, 2, 3, 4, 5, 6, 7, 8 in, like we saw. Or like we guessed, I guess. And I guess we can also do the subtraction here. So we can say print this guy minus, oopsies, minus the old stack pointer that we were looking at before, which is this guy here. Which is negative 32. Oh, I multiplied by 8 and so forth. Fuck. So it's here, we should be saying 40. Let's run without GDB again, just to like simplify the run thing and see if it works with the fixed number there. Okay, so that's good. The kernel's now running reasonably. Nothing's like horribly fucked. So that's a real good sign. And now let's look at our sample process scan. And were we supposed to print? No, all we're doing is exiting here. So now if I call print and exit, I think we're back in like the working state. Where we should see hello world and everything. Mwah! Little hello world here. The rest of our kernel still runs. That's pretty fucking sick. So to recap, why it's so exciting that we're not seeing any crashes here is in our sample C program, we implemented a panic, and here we tried to run it. If we comment out this exit and we run, we make it to that line in the panic in the thing we loaded. He says, frowny face, I'm angry and sad because I crashed. Here we implemented this exit call, which is like doing some like hacky shit. But basically saying, hey, take all of the registers and your stack pointer from when you started running the program, and when you call exit, just reset them to that state. And we like took a bit to figure out like how you're supposed to do that. We forgot to like back up the registers, but once we backed up the registers, it's kind of like working reasonably well. Which means that like I was trying to think about like multi-processing at some point. Like at some point we're going to have to, if we want to implement like syscalls that are asynchronous, the kernel is going to have to be running like concurrently with the process itself. And so what we've kind of proven here is that we know how to like jump between execution contexts. So what we could theoretically do is back up these, like keep track of like the stack pointers and registers for each program. And when we want to switch between processes, all we have to do is like pick the set that we care about, jump to and pick and like restore those ones, which is pretty sick. So that's exit done. That's exit, and that's print, panic. And so I guess let's say that we wanted to run like a program. It would be kind of let's just do one last little thing where we try to paint the screen, right? I think that's interesting. We can say we'll draw to the screen as part of a process. And if that works, then I think that we can kind of say that we understand how we're going to pipe things in. Now, obviously, I want to, like, this syscall interface is like, there's a lot wrong with what we're doing right now, right? We have like no protection at all, right? Any process, since everybody's using the same physical memory with no protections, anybody could just jump into the kernel. But we're kind of like assuming right now that we only have reasonable actors, and reasonable actors is only me, so we can assume that for now. Yeah, okay. So let's say that we're at maybe at like 1 hour 25 and 38 seconds. We're going to start trying to like draw to the screen from loaded process. And that'll be the last thing we do here. And so maybe what we'll do is we'll just pipe in one more function to this vtable. Draw. And we'll take in a X position and a Y position. And we have to implement that same thing on the Rust side. Actually, before we do that, let's fix our bindings. So let's actually say, oh shit, 26, 25. Here we go. And we're gonna say implement vtable bindings. Let's do that first. Because I don't want to have to I feel like there's like a good chance of me fucking this up. So what we're going to do is we're going to pull in this like bindgen library or like compile time thing. So we're going to look at bindgen in docsrs. And let's see. Yeah, so I think this is what I want. Rust provide C++ header file, receive Rust FFI code. Okay, yeah. So here, for now, I don't know where it's going to live. So we're going to res sample program vtable .h. And we'll just take the vtable from our sample and shove it in here. And then from here, we'll include vtable.h. Great. At this point, everything should still work. Wonderful. We still see our hello world. We still see the kernel continuing. And now what we want to do is in our build script, we want to run bindgen. So we're going to pull in a dependency, which is bindgen, but at build time. So we're going to say, I think it's build dependencies. And we'll just look at bindgen is equal to 0.69.1. I struggled in the past with running bindgen on NixOS, but it turns out that there's this like one-liner that you can do to fix it. It's in my Nix, in my shell, edit shell.nix. There's like, you can say, I want like a native build inputs that's Rust platform dot bindgen or something. I'm gonna have to look this up. Rust bindgen NixOS. Nix Rust documentation. Rust platform, I think is what it's called. GitHub. I'm just looking for like, I saw this. Here we go. This is what I'm looking for. I saw something that was like bindgen hook. Yeah. So here I just say this, and then when my Nix shell starts, it'll run this hook that sets up the environment so that bindgen will work correctly. But I wonder if it will work for, I don't know if it's gonna like generate the right code for an x86 machine, given that my host is x64. But we'll see. So they do populate this bindgen extra clang args for me, which is great. But all of these guys are wrong. So we'll see. We'll see. We'll have to like keep this in mind and come back to it. But I think that probably for this particular structure, it'll probably generate something sane. So I'm not too worried about it. So we're gonna say bindgen, and we're going to, where was I? Bindgen builder. I'm gonna say let bindings is equal to bindgen builder. And what am I going to say on here? I'm going to say the header is the header. So we're going to say header is at res sample program vtable.h, I think is where we put it. And probably there's nothing else we have to do. So we'll just generate. And we'll say expect failed to generate vtable bindings. Then all we have to do is we have to write those bindings somewhere. So we're going to say let bindings output file is equal to format. We're going to take the existing output dir and we're going to append vtable.rs, I guess. That seems reasonable. That's like a fine name. We'll say bindings write to file bindings output file, and we'll say please crash if that didn't work. Failed to write vtable bindings. So now when I run this, we should end up with some bindings, but he's not happy because no such file or directory at build.rs13. What the fuck? Am I missing something? No such file or directory. Oh, source env. That's right. Because my compiler isn't available until I do that. Cool. I didn't type include correctly, so let's just sample.c. Include. And that's actually bringing up a good point that in my build script, I actually have to say rerun if changed. So I think it's like print line cargo rerun if changed. And here I just have to shove in this guy. That was still incorrect. Hey man, sometimes we suck, okay? That's so funny. Include. Thank you. And we'll say, I guess we'll stick this in a variable. So we'll say let sample files equal to, or sample C is equal to this. And we'll say sample C. This guy needs to rerun chain sample C. And probably we would actually have to rerun if anything changed in the directory. So I wonder if we can just say rerun if changed. I don't know if it will do this correctly if I specify like a directory instead of a file. Cargo rerun if changed. Directory. Rerun if changed. Tells Cargo to rerun the script. Rerun the build script if the file at the given path is changed. Currently, he uses the file mtime. If the path points to directory, it will scan the entire directory for modifications. That's what we're looking for. Sick. Okay, cargo build. And in sample.c line 7. Warning, no return function does return. What's he fucking bitching about? This... Oh, so this is in the bindings generator. It assumes that exit is a no return. So how do I, like, annotate this with no return? Can you, like, no return function pointer C? Let's just see. Alright. I wonder if this goes here. Warning, assignment function pointer from unqualified. And so I guess in vtable.h we have to do the same thing where we have like attribute no return this. Ugh, that's annoying. How do I, like, ignore this? Because it's, like, just doing something stupid where I guess we'll just call this exit 2. And I think that will probably fix... No? I thought that would fix it. So what doesn't he like now? What is he saying? Bind gen context main panicked. Build didn't run. Can we run like rust backtrace is equal to 1? So this is at bindings generate. Bind gen context new. The thread main panic. Invalid flag syntax, unrecognized flags, invalid flag arguments, file IO errors, host versus target architecture mismatch. That seems likely, but also there's like nothing... Like, it shouldn't know about that. Oh, it does know that I'm fucking generating for my i686 Elf. Ugh. And Clang doesn't support that architecture. Okay, so I guess for now we'll just live with the duplication. That's fucking annoying. So we'll just say fail. And we'll just jump back into... Well, do I really want to like draw the screen? That was kind of some like just extra stuff, but maybe we won't do that now because we're at an hour and a half. Maybe it's okay to call it there and think about what we want to do tomorrow. So I think probably tomorrow I want to look at I've been wanting to look at like IOU ring and try to like use that as inspiration for a syscall API. We might also look at multiprocessing. I'm not really sure which one of those I want to look at first. Either like yeah, because like theoretically I should be able to run multiple in a row. I guess if we figure out that we're going to do channel-based syscalls, we'll need multiprocessing to do that. But we could look at IOU ring first. So not sure. We'll do one of those two tomorrow. If you liked what you saw, I stream most days around 1 or 2 o'clock Pacific time, and I try to go for some time between like 1 and 2 hours. It totally just depends on if the what we have to get done that day. Going over 2 hours is, you know, a little long for a YouTube video, and less than an hour is like not very interesting. So that's what we do. There's a GitHub linked in the Twitch description as well. And there's a Discord linked in the Twitch description where I post like when I'm going to be going live, and people have been talking about like OS dev stuff, whatever. Feel free to pop in, say whatever. If you're watching on YouTube, there's a Twitch link in the YouTube description, and that just lets you, if you want to come in, say hi, talk and chat, whatever. Otherwise, that's all. Thanks for watching. Catch you on the next one. Bye, guys. Shit. Bye.